All right, welcome to the Explainer. Today, we're skipping the high-level stuff and diving right into the blueprints. We are opening up the engineering specification for a piece of technology I am convinced is the key to unlocking the future of regional air travel. We're talking about the Thermal Propulsion Unit for advanced air mobility. So, this is the dream, right? We've all seen these incredible images of what regional air mobility could be. But to make these aircraft a real commercial reality, there's a massive problem to solve. And it's not a small one. It's a problem rooted in the fundamental laws of physics. Specifically, how much energy you can pack into a battery.
And here it is. This chart shows you everything you need to know. Aviation fuel, your standard Jet A, packs over 40 times, 40, the energy of the best batteries we have, pound for pound. That huge gap means pure electric flight is stuck at maybe 20, 30 minutes tops. That's just not enough to connect cities.
So how do we get around it? Well, here's the plan. We're going to walk through the architect's blueprint for solving this, piece by piece. We'll look at the problem, the hybrid architecture we're using to solve it, how it operates, the major engineering hurdles, the absolute focus on safety, and finally, how we prove it all works. Okay, first things first. Let's really dig into why this energy gap isn't just some small technical hurdle. It's a total showstopper for any serious air taxi business. The problem isn't just about how long you can stay in the air. Think about it this way. For a pure electric plane, the batteries you need can eat up 60% of your total takeoff weight. So imagine a 4-seat air taxi, where 2 of those seats are just batteries. You can't sell a ticket for a battery. The business case just completely falls apart. From a systems perspective, the conclusion is unavoidable. Right now, a hybrid powertrain is the only viable path forward. So if hybrid is the answer, what does that solution actually look like? Let's get into the architecture, because this is where some really elegant, really smart systems engineering starts to happen. Okay, take a look at this. This is the P13 system. It's a series parallel hybrid design, which is a fancy way of saying it gives you the best of both worlds. It can act like a generator, making electricity, or it can have the engine and motor work together to turn the props. And at the heart of it all, the star of the show is the Thermal Propulsion Unit, or TPU. Think of it as the central energy hub for the entire aircraft. Now, I want to be really clear about this. The TPU is not just some engine we grabbed off a shelf and bolted on. No way. It's a highly integrated, intelligent power module. It's designed from the ground up to decide, okay, right now I need to spin the propeller directly for max efficiency, or nope, time to switch gears and generate electricity to top off the batteries. Now, this is where it gets really cool. The real genius of this design is how it seamlessly switches between 5 different operating modes to optimize for power, efficiency, and safety during every single part of a flight. Check this out. Mode 0. That's your cold start. The electric motor fires up the engine in under 5 seconds, even if it's freezing out. For takeoff, you get an e-boost, where the engine and battery work together for maximum power. Then you settle into Mode 4, your super efficient cruise. And the big one? Mode 5, the air start. That's your critical safety net. The ability to restart mid-flight isn't a nice-to-have, it's an absolute must for certification. So this all sounds great on paper, but trust me, it wasn't simple. To get here, the engineering team had to basically go to war with physics on 2 major fronts. First up, altitude. As you go higher, the air gets thinner and engines start to choke. They lose power. The solution is a turbocharger, which forces more air into the engine, guaranteeing you have full power when you need it. The second problem is vibration. Piston engines shake violently. The really brilliant thing here is that the P1 electric motor is used to create anti-vibrations that literally cancel out the engine's shudder. It's like noise-canceling headphones for the entire powertrain. Now, in aerospace, you don't reinvent the wheel if you don't have to. You make smart, strategic choices to reduce risk. That's why the team chose a proven engine core, the Rotax 916IS. This thing already has fantastic performance at altitude. It's lightweight, and this is the real kicker, it already has a certification baseline with ESA. That one decision saves years of work and headaches. Okay, let's talk about some key numbers. These aren't just goals or targets, they are survival thresholds. Take that power to weight ratio. If you fall below 1.8 kilowatts per kilogram, the entire hybrid system becomes what we call ineffective payload. It's just dead weight you're hauling around for no benefit at all. You have to hit these numbers. All right, let's get to the most important part of any aircraft design, safety.
because all the performance and efficiency in the world mean absolutely nothing if the system isn't safe. This is all about designing for zero failure from the very beginning.
Safety here isn't an afterthought, it's the foundation of the whole design. You see that firewall? That's made of titanium. It's designed to withstand a fire hotter than lava, 1100 degrees Celsius for a full 15 minutes. That's a wall of protection that separates the engine from the batteries and, most importantly, the people in the cabin. And the whole philosophy is based on layers of protection. There's a Kevlar shield in case the turbocharger fails. The engine's computer, its brain, has 2 separate power sources, plus its own backup generator. The whole point is that no single failure can ever lead to a catastrophe. In this system, if you lose the entire TPU, it's a major event for sure, but the plane can still land safely on battery power alone. That's the key.
So we have this incredible blueprint. We have the safety design baked in, but how do we actually prove that it all works as advertised? That brings us to the final exam, the acceptance blueprint.
You don't just bolt this onto a plane and hope for the best. It's a rigorous 3-stage process. First, we test the engine by itself on a dynamometer. Then, it gets integrated into what's called an Ironbird, a full-scale replica of the entire powertrain on the ground to make sure all the parts talk to each other correctly. And only then do we throw the worst conditions imaginable at it: extreme altitude, intense vibrations, and icing. And this right here is the final scorecard. It is black and white, it's pass or fail. Does it deliver 160 horsepower at 15,000 feet? Yes or no? Can it restart in under 5 seconds in the freezing cold? Yes or no? Does it overheat during a max power climb on a hot day? Yes or no? If it fails even one of these tests, it doesn't get delivered. Period. So when you boil it all down, the big takeaway is this. Success in hybrid aviation isn't about just taking an engine and a motor and sticking them together. The real magic, the secret sauce, is in the deep, complex engineering that solves the coupling of heat and electricity, making them work together as one seamless, intelligent system. So this blueprint, it effectively cracks the code on the powertrain. That's been the biggest engineering mountain to climb. The question for the industry is no longer if the technology will work, but when it will be part of our daily lives. The next frontiers are things like air traffic control, building out infrastructure, and of course, public acceptance. The engineering is becoming reality, and that is how the future takes flight.